Well, good morning, everybody. It's I've only had one coffee, I guess, so I'm not exactly paying very much attention. For this talk, what set this up was the thinking that increasingly over the last few years we've seen more and more interest in data science and the role of data science, data engineering in software development. And we thought it would be interesting to try and look a bit at what the similarities and differences are between regular software development and this new world of data. And I could talk about this, but the problem is I don't really know anything about it because I'm not got any background in data science and data engineering. So I do what I normally do when asked to give a talk about a topic. It's I actually find somebody who knows something about the topic. And I discovered M here, who is... The official Thoughtworks title is Data Witch, but I realize there's a little bit more about it than that. So how did you get into data science?
Yeah, hi everybody, and hi Martin. So I got into data science. I started studying mathematics in my undergraduate school, and somehow I ended up with a degree in Buddhist metaphysics. And later on, I went to graduate school and studied economics. And the field in particular that I was studying in the economics world was called Neuro Economics. And Neuro Economics is the practice of looking at the chemistry of decision making. Economics in general is all about human decision making, and I was looking at what is the chemistry behind this? So we would stress people out and look at what their brains were doing in an fMRI, or we'd give them hormones and then watch how they behaved inside of a simulated environment like a laboratory or a game. And so I was doing a lot of statistics, and I was doing a lot of computer programming in Python and Stata and some other weird languages at the time. And when I left school, I had a bunch of statistic knowledge, a bunch of computer science knowledge, and I taught myself a little bit about Spark and a little bit about infrastructure. I called myself a data scientist, and this was many years ago. Somebody believed me, and that was my job title, and that's what I did at work. And eventually, I guess at some point, it became true, right? So now I've been doing data science for many years in a couple different fields.
The thing about the title is wonderfully ironic, because my job title is chief scientist, and as I always say, I'm not chief of anybody, and I don't do any science. At least you have done some science, which is something at least. So yeah, for those who haven't cottoned onto this is going to be a kind of conversational Q&A kind of thing. We haven't bothered with any slides because I'd be honest with you, I find this whole thing of giving talk over Zoom is to be totally weird. And for someone who hates giving talks anyway, it's even, I think, worse doing it this way. But with the conversation, we hope we manage to get through it without me actually shooting myself halfway through the talk. Anyway,
let's see what happens.
I mentioned at the beginning, we've talked about this data science and data engineers. And one thing I do hear a good bit is this distinction between data scientists and data engineers. So how would you describe that distinction?
Yeah, so the difference between a data engineer and a data scientist, when a data scientist is doing their work, they're often not necessarily concerned with exactly where did the data come from. Of course, they're concerned where did it come from because they want to have information about the background of the data, but they don't care so much about getting the data from the user, from the sensor, from whatever to their machines. And what they care about is, I want to pull the data into my machines. I want to be able to analyze the data, look at the data, create models, fine-tune my models, and get some answers. So the data science field is pretty much within this area of once the data exists. And data engineers, I would say, are people who they're working on the platform to enable the data scientists to be able to do their analysis. So data engineers might be working on making the data available very quickly, making the data, maybe they're doing transformations, consuming it from other upstream providers. Maybe they're working just on making sure that the algorithms are able to stand up on the AWS servers or whatever it is. So it's comparable to the divide between infrastructure and computer scientist or software developer and infrastructure developer. And there might even be overlap. There might be people who do the entire gamut who are working on data engineering as well as data science, and there can be organizations where they're completely separated.
So given that, the data engineering side sounds more familiar. Obviously, there's a lot more data being schlepped around than one would do in many traditional application development environments. But the data science thing sounds kind of, in many ways, some of the more different part of it. In particular, there's obviously a lot of statistics in there. So if you were looking, so what kind of statistical skills are needed? Do you just need to be able to remember off the top of your head the difference between a Pearson's chi-square test or a Fisher's exact test? Or, is that the kind of stuff you have to learn all about?
So in my opinion, exactly the type of question that you asked, those are the questions, the gotcha questions that people will give on data science interviews. And often when I hear a question like that, I think maybe I want to walk away from this engagement. Like, I don't think that that's a very important distinction to have, or like piece of knowledge to have right in RAM. Of course, being able to, having done the research could be useful, but what the important part is to have the statistical intuition to be able to think like a statistician. And what this means is to be, what I would say is to have a healthy paranoia about how the data can trick you. Maybe you could also just use the word skepticism. For me, I describe it as being able to see the world in distributions and in probabilities. To give an idea about these statistical intuition, I'll talk about a story of a man named Abraham Wald in World War II. He was looking at the fighter planes that would come back from enemy lines. And these airplanes were perforated with bullet holes. And the generals would look at these airplanes and say, oh my gosh, they've been shot up. Like the wings, like big parts of the wings were just like completely like Swiss cheese. And they said, these are the big parts of the airplane. They're big targets. We need to reinforce them. And we need to make sure that the bullets don't penetrate the airplane. And this guy, the statistician, Abraham Wald, was like, he was able to have this statistical intuition to say, wait a minute, but these are the airplanes that came home. We have no data of airplanes who have perforated engines, even though that's a smaller surface area. What the generals are involved in is something called survivor bias. So they are looking at things that were, they only had data from people who actually flew home. So being able to turn the problem around and chew on it and look at it and say, wait a minute, what is the actual important piece of data here? Yes, I see a lot of bullet holes, but what am I not seeing from all the data that I'm looking at? I think that that's a really crucial skill to develop. And it's indeed a skill. It's not a thing that you're just born with. It's like anything else. Maybe you can get it in grad school. Maybe you can get it from studying by yourself and doing practice with other people. The other example is something called Simpsons Paradox. And this is the paradox that when you look at data in the aggregate, it tells a different story often than maybe the opposite story is when you break up the statistics and look at them individually. It would take several minutes to explain. I'm going to skip over it, but what I do want to say is like the general statement is that, for example, babies who are born to mothers who smoke are often underweight, right? And so if you look at the statistics of children who are born to mothers who don't smoke and children who are born to mothers who do smoke, the children who are born to mothers who smoke and they're underweight are more likely to survive to adulthood than the babies born to healthy mothers who are born underweight. And there's a lurking variable that makes this not apparent. Why would it be that babies born underweight to smoke, you'd think that those babies would be the less healthy ones. But the trick is that most babies born of smoking mothers are underweight, and so that's kind of the expected average for them. But babies who are born from mothers who don't smoke, who are underweight, maybe have some other underlying issues. So it's not clear immediately from the data what's going on. So this is my big thing is yes, you can learn different tricks and different tools, but ultimately being able to tease apart the data is really what's important for me in a data scientist.
Yeah, I really like that story of the returning aircraft. I came across that first, I think, in one of my favorite books, Thinking Fast and Slow. and I'm blanking on the name of the author.
Daniel Kahneman.
Kahneman, yeah.
Yep.
And I really strongly recommend that to anybody because it really brings out a number of these sort of statistical illusions, and they're really important, I think, for developers to know about, certainly if you're going to be looking at numbers, but I think generally anybody. I mean, just look out at the world at the moment. We're dealing with a major crisis from COVID-19, and you're spending a lot of time looking at the stats and trying to make sense of them. I mean, we're having this particularly strong blast about it at the moment in the United States because numbers are doing crazy things, and to try and make sense of what's going on, you need that. You don't need clever statistical tests. You need what you mentioned, that intuition. There's a well-known statistics writer who focuses on political projections called Nate Silver in the US, who's very good, I find, for looking at US politics. And he made this comment about how if you want to be good at data science, you should spend 49% of your time developing your statistical intuition, 49% of your time understanding the domain you're looking at, and the rest on statistical methods. And I know we talked about that early on, and you definitely nodded with that view of how to take things.
Yeah, and it's hard to juxtapose that with the reality that a lot of times we spend a lot of our time looking at bad data and trying to clean it or trying to prepare it and doing the process of making the data suitable for us. But definitely, I think that if you, especially as you're trying to improve yourself, those are definitely really important focus points.
Yeah, I mean, and I'm thinking here very, very generally. I think generally most humans could do much better at developing a statistical intuition and an understanding of numbers. I've often wondered whether I've always been a gamer, as you can see by all the games behind me, and played games from a very young time, and I got very used to probabilities doing that. And I often wondered whether that helped me myself understand probabilities better. So maybe that's a technique one could use. I don't know. I don't know that there's anybody who's really tried to assess that. So anyway, moving on a little bit from our general feelings about understanding data. When you talked about earlier on about what a data scientist did, you talked about building models. So when we're thinking about software development, we build code systems, but in data science, the focus very much is about building models. So what are models and how do you go about building them? What is the process in that data science world?
Yeah, so my favorite model is the linear regression, and this is 100 years old, and it's really nice because everybody's seen it, and you can really picture what it's trying to do. You have an XY coordinate, you have an XY plane, and you have a bunch of dots on that, and then you fit a line that is the optimal distance from every single one of those points. And you can actually generate this through machine learning, but there's even just an equation that you can use to generate this line. And none of those points will ever touch that line. It's like a mathematical impossibility that a point and a line they'll actually perfectly interact if we're sensitive enough in our measurements. But that line is the best linear description of the data. And you can take this idea and export it to any model that you're going to be producing that has any predictive power. There's other things you can do with machine learning where you can cluster things and that's not necessarily making predictions, but many of the models are trying to predict. They're taking a set of historical data and they're producing through some algorithmic method, a way to map that to the future and extrapolate. So if I give you another dot on the x-axis that I tell you, here's the x value, tell me the y value, you can just look at the line and say, here's where it will be. And of course it will be wrong, but it'll be the best prediction that we can get given a linear model. So in general, when we're talking about models, we're talking about taking historical data and turning it into a prediction through some algorithm. I think another way to think about models is you can think of them, so just as the linear line is never going to match those points, that every model is it's a lie that we tell ourselves about the universe, and it's useful in the right context if we make it correct. So a good example of this is to think of the Mercator map. This is a map that you see every school, every elementary school in the world has probably a Mercator projection map on their wall. And so kids grow up thinking Iceland is this huge icy wasteland and Africa is not so big. And so it's a lie about the size and the relative distances between places in the world, but it's a really useful model of the world if you're trying to navigate by the stars in the 1700s. So there's other ways to tell the story, and it depends on what story you're trying to tell and what problem you're trying to solve. The way that we do this is usually, nowadays as data scientists, we're doing this, we're creating the models by looking at the data in an interactive, like, they're called notebooks. It's like when you open up your browser and you start typing in some code in JavaScript, or you type Python into your terminal, and you can start writing code right there. We have these notebooks that enable you to do that with a little bit more intelligence, to be able to make visualizations and change a variable that you instantiated already. And so the workflow for us when we're doing data science is we load our data in, we start constructing our model. Oh, maybe I need to change a variable or add a new column or something like that. And I do it in this interactive workbook. And once I've caught my equation, if it's a linear regression, or I've got a pickle file if I'm using some Python library, then I can save this model, and it can just be saved on my hard drive, or it can be uploaded to the cloud. But then I can query it and get the corresponding value. So I give it data that looks like the historical data, but it's a new piece of data. It's a new dot on the x-axis. Or I say, here's the x value, please give me the y value, the prediction. And then given that, the model will be able to give me my answer.
The interesting thing about this is that actually ties in quite well with decisions you make generally in software development about representation of data. I mean, we talk a lot about choosing data models or data structures, particularly in larger organizations, there was a big push, certainly the way I was taught back in the 80s, said we need to come up with a single model that will handle the whole organization's data in a consistent way that works for everybody. And what I discovered, and hopefully more and more people also discovered, was that was just a fool's errand. I mean, there is no one single representation. It's like, as you say, with the global map. If you're going to project a map, a spherical world onto a flat surface, different projections work for different purposes. And that's what we're doing with just representing data at all, is we're reflecting that different back and forth. So we have a similar issue of choosing models to represent things in a simply static data style.
Yeah.
How do you explore what models to use and build? I mean, how do you come up with what kind of approach? I mean, you've talked about a simple linear model. You've also contrasted it to machine learning, and certainly for many people, the whole data science thing is just coming up with machine learning models. But linear models also have a role, right?
Yep. I like to joke about this in every one of my talks, that I think the most pressing question in data science today is, couldn't we just use a linear regression model for this? But it's true that there are cases where you might want to use another model. The reason I ask that question is because I think that a little bit will go a long way. And most of the time, it's going to be quite important, if not more important, to be spending time getting feedback from your users, learning if you're positioning the model in the right way, talking to the right people, being able to get the feedback as quickly as possible. And if you can do that, if you can get I don't know, 50% of if you can get some accuracy, I don't want to put percentages on it, but if you can get some good results with a linear model and you can get it up to date, that's so much better than making the perfect model that's using a convolutional neural network that takes 3 years to develop. And I hope it wouldn't take you 3 years to develop that model, but especially when your model will be more powerful when you have historical data, you want to get your model out there as fast as possible and start talking to customers as fast as possible and iterate on the data that you're collecting, because once you get it out there, you'll realize, oh, we're asking the wrong question, or we're not collecting a vital piece of information that we need to. So let's change the input pipeline. And then once you feel like you can't squeeze your linear model anymore, or your logistic model anymore, then let's bump it up in complexity, or let's start worrying about the parameters that we're passing. Nowadays, it's actually quite easy to start with a more like a machine learning model. You can start with a linear, like you don't have to start with a linear regression. You can start with a random forest or a decision tree or a naive Bayes. It depends on what type of data and what type of answer you want to have. But any language that you're going to be using to be doing data science will have supported libraries to enable you to do machine learning out of the box quite easily. But then there's always questions of how deep do you make your neural network? How many trees do you plant in your random forest? These are called hyperparameters, and you can tinker with them forever. But I am always going back to the point of get it out there fast. These are minor changes. Usually you'll be able to get some more power out of your model, but it needs to be asking the right question, and you need to be collecting the right data first.
So there's certainly a parallel there with software development, certainly the way that I look at it, in that you want this close relationship between the people doing the programming or doing the modeling and the people who are getting the value from that. The heart of the whole agile thinking, which is something I've been involved in, to me, if somebody who asks me what's the key to agile thinking, it's about breaking down the barriers and making fast feedback loops between the people who are producing the software and the people who are getting value from it. And I use that term getting value fairly vaguely because value can come in all sorts of different directions. So it's interesting to see it's a similar kind of situation within data science. You have to, so do you find it's a real struggle getting to make those links between the data science people and the users, customers, everybody else who's getting value from the data, but there are barriers in the way that we find with software development as well?
We find with a lot of clients and also talking to other data scientists at meetups and conferences that a lot of times data scientists are in a silo. They're able to work with the data they have, and they're able to do some analysis with what they have, but they're not integrated within the software development teams or within the companies in a way that enables them to be able to ask more meaningful questions or do more prioritization with their stakeholders in a way that using their expertise to deliver more value. This is a problem that we've found in lots of different fields.
So we talk about building up the model, and I'm assuming that's done in a relatively closed environment as you're tinkering with. What kind of changes then shift as you then get that model and put it into a production setting where it's actually influencing people's decisions?
Right. So think about the model in production as just a black box. It could be a jar file or a pickle file or a binary. It's some binary that when you provide it data in the right shape, it gives you an answer in the right of its prediction. So I could hand you a model as a software developer, and I could tell you this: if you plug in this JSON or a CSV that looks like this, it will give you a number. And that's usually what it means to have a model in production, is you tie it together with a REST API or something. And so somehow a query comes in, says, here's the X value, please give me the Y value, and then the Y value comes out. How do we get it there is the hacky way is you save the model from your local machine and you upload it to AWS, and then the pipelines, if you have pipelines, they know how to pull down the most latest model. If we want to do it the right way, the way that I would prescribe is to, when you've done all your data exploration, you've figured out exactly the shape that the data should be in, you've trained the model, you found the right parameters. Extract all of that code that lives in your very messy spaghetti code Jupyter notebook and start plugging it into your real IDE and begin writing tests right away. And once you've written a test, give that chunk of code, then make it a named function or like if you want to do classes. But right away, the second that you've gotten something that seems to work for you, then you put it into tested code. You can either have it so that when you push this code, you produce the model in the pipelines, or you can have a setup where the model is like saved in a separate way than directly through the code. There are benefits to either way, but one of the simplest ways is truly to have every time you make a change to your code, you produce a new model depending on how long it takes to make the model. And that model gets uploaded the same way as if you like pushed JavaScript, compiled JavaScript or something else. It's saved in a separate place than your version control, and built and trained every single time.
Now you mentioned version control there, which is obviously something that is a core thing for any software developer, but there's particular challenges, I gather, with the data science world when it comes to version control, because there's a lot of data you've got to keep hold of, right?
Yeah, so the data definitely is something that you can't, obviously you can't fit the data in version control. Another thing that many people don't think about is that you can't fit the model in version control either, usually. So this algorithm, I give you input, you give me output, it could be a 25 gigabyte gig Java jar, and this is definitely not a thing that you can just commit to version control. And one of the principles of continuous delivery is to be able to roll back at any time. So we need to keep our models versioned in a separate place than our code. And if we're not using the strategy of creating the model every single time we make a change to the code, then we can start to have some decoupling issues. Also, the model itself is built based on the shape of the data. So if I'm giving you data that has, let's say it's a CSV file with 10 columns, that's what I train my model on. If I add another column, then I try to put it into the machine learning model. The machine learning model won't know what to do with that. In many cases, it will just throw an error. So the schema of the data needs to be also somehow versioned. Maybe the people who are working on this don't have control over the schema of the data. Maybe it's an upstream API. Maybe we decide that weather.com is a fine enough API. We're going to use weather data to do our predictions. And if weather.com makes a breaking change in the JSON package that they deliver us, then our model has been broken. And so being able to roll back, considering that our model and our data need to be compatible, and the code that gets the data the code that transforms the data into a thing that the model can use is also a thing that can vary. Now we have 3 different variables that move independently of each other. And it's a quite difficult problem to solve. And this is a thing that, to my knowledge, I've talked to lots of different people in conferences, and everybody finds this to be a sticky point. How do we keep track of the data version, whether it's the schema or the values of the data and the model and the code? How do we couple these together loosely enough that they're liberated and they're not constrained by each other, but tightly enough that we're able to do our rollbacks or identify when there's a mismatch?
So another thing you mentioned in your description earlier on was the role of testing. So testing, again, something that matters a great deal to me. How does that look in this data world?
So the classic way to test when we're doing supervised machine learning is, as I said, we take a bunch of data from the past, we create our model, and then we're able to make a prediction about the future. And the way that you can validate your model is to withhold a random sample of the data, of the historical data. So I do a random sample and I just put all those data points in my pocket. I create a model, and then I take those data points out of my pocket and I plug it into the model to see how would it have predicted this value. And then I can get some score out of that. And I can set that as my baseline. Any model I make is going to need to have such performance, so much accuracy that it needs to be at least this good or better or something like that. This is the classic way to do it, is to have a withheld data set and compare your model to the ground truth using historical data. As I said, testing, it's it's tempting when you're using these notebooks and working in this interactive REPL to write a bunch of code and maybe copy and paste it into another file without writing the tests. It takes an act of will to, I've got such an exciting finding, I've got such an exciting visualization, I've created a really cool model that I've been struggling with for the last 2 weeks. It takes a strong act of will to turn that into something that's tested. And you can also give yourself sanity checks or smoke tests where you have some contrived data that you pass through to make sure that things are still compiling or that errors are thrown the correct way. And then you can also do things where you're testing when things are when the model is living in production. I can't tell if I'm okay. No, the connection didn't seem to be working. But you can also write tests for things that are living in production, so that maybe you could have a shadow algorithm. That's, you have your data, your users, and they're doing actions or performing things, and you're interacting with them. Because you're interacting with the way that the users behave, your model that's running in production might not be a valid way to measure its own performance, because it's affecting the real world. But you can have a shadow model that's just hanging out in the background and calculating what it would have told the user, or what it predicts the user would have done. And this can be a way to keep yourself certain that your model is connected to reality, and rate yourself about how well your model is predicting things.
Sorry, so one of the things that I found really fascinating when I was talking to people about this was how, I mean, one of the jokes about software development is that we talk about this activity called maintenance, but software doesn't rust, right? So maintenance is kind of silly, because what we're doing is usually we're adding new features and things of that kind. But when talking with some of my data science colleagues, I realized that in a way, these models do rust, and that they deteriorate over time in a way that we kind of don't expect from a usual software development background. So could you talk a little bit about that effect and how we deal with it?
Yeah, definitely. So the interesting thing about these models is, because they're trying to be a little lie that's useful, that's lying about the state of reality. And just as much as we struggle with data that is incomplete or incorrectly collected from sensors or transcribers or whatever, just as much as we struggle with the bad data that could be tripping us up, we also struggle with the fact that the world that we're trying to model is rapidly changing in many different ways that we can't predict. So there's randomness just inherent in the reality that we're trying to model. And this produces a lot of problems for us. My favorite example would be to imagine trying to train a natural language processing model. And we're trying to understand sentiment of written word or transcriptions of spoken word. And if I train that model based on Amazon reviews from 2020, or all Amazon reviews of all time, the predictive power will not be that great if we're looking at data from like conversations from love letters from 1890 or something like that. The language changes over time, and the models need to evolve with that. Another example of this is when you're dealing with credit card fraud, and you're trying to understand if the behavior of a certain person, is this purchase fraudulent, or is this a thing that somebody actually wanted to purchase? And so you create a model that works for most of your users. And then if you discover that one major retailer had a credit card breach of 200,000 people, and now there's 200,000 cards floating around in the black market, the model suddenly doesn't work anymore. The data is still fine. The schema of the data hasn't changed. The model was working yesterday, but because reality changed, we're no longer able to predict with the same way as we used to be. My roommate works predicting traffic, and since Corona, there's been a whole different world of how do you, all the models are broken, because there used to be cars all the time from people driving to work, and now there's just every model that they've had about human behavior in their context doesn't make any sense anymore. So this is definitely a problem of model deterioration. I like the idea of rust. And you can use as I said before, you can have tests and running in the background. You can make sure that your model is performing a certain way relative to the actual behavior of the users or the actual historical data, but it'll be an ongoing task to make sure that the model stays up to date, or that the model is retrained given the new piece of information. And especially thinking about the way that the trends change, maybe you might have to, rather than just retraining, also update the data pipeline or the features that you're focusing on when you train the model.
And part of the issue of a rusting model like this is also understanding how it's actually providing that value. We talked about earlier on about how you need that close contact when you're developing the model initially. When you've actually got the model in production, you've got this same thing. How do you know that the model is actually providing value to the people who are supposed to get that value from it? What kind of techniques do we use to try and determine that?
I would say that these are probably very similar to the techniques that exist in the computer science world as it is, that the data scientists, when we develop things, when we work on an experiment or we develop a new model or implement or operationalize a new model, that we should be doing so with key performance indicators in mind. We should have a goal, and we should be able to say what success looks like. And we should be talking to the stakeholders, probably also users and everybody who, connected to the business. There could be that we should define, what does it look like for this to be successful, and how will this serve our customers should be part of that conversation.
But that also, I mean, that's part of the thing, is how do we provide value? But also, I think one of the, obviously a concern that's been increasingly people are paying attention to is, how do we tell when these models are actually producing harmful information? I mean, we had in the United States just a few days ago, I think, the first case of somebody who was arrested based on facial recognition, had absolutely no connection with any kind of crime whatsoever, but the facial recognition picked him up. Unsurprisingly, he was dark-skinned, which is, of course, a problem that we see in society generally, and reflected en masse with AI, because, of course, as I always learned as a kid, to make mistakes is human, but to really foul things up, you require a computer. And it just inflames whatever existing situation exists. So that puts another challenge upon us as software developers. I mean, we certainly want to make sure we're providing some value to people, but it's also really important we don't do any harm. And I mean, what kinds of things are present in the data science world to try and address this? And are people getting a hold of that issue and dealing with it more seriously now?
This is a problem that the entire tech world is facing. And certainly, though the first arrest, I guess, happened this year, we've also been seeing other uses of AI or of machine learning that have been, I would consider harmful or wrong for many years. I like to think of, so I want to remember that your question was, what tools are we using, or how, what tricks can we do to prevent this? But I want to think about, in the way that I would model this in my head, brings me back to a story of genetic programming, where we teach programs, we give them all the tools to write their own software, to write their own algorithm, and then we give them an optimization problem and let them solve it. And what happens sometimes when you use genetic programming to, say, play a game with somebody, there's a lot of unexpected things that happen. So the chess playing robot is trying to learn how to play chess based on playing lots of games of chess. And what's come up, researchers have found over and over again, in certain circumstances, if they give too much freedom to the algorithm to evolve, it will do things that are completely unexpected, but very obvious when you think about it in retrospect. So my favorite example is the chess playing robot that will just never make a move. Once it becomes that robot's turn, it will just wait. And it knows that the human opponent, it can wait longer than the human opponent. And so every single time it's that robot's turn to go, it waits, da, 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 da. Eventually the human leaves and the robot has won. So it has a flawless victory of never having lost to any humans because it just waits. And I always think about the environment that, so this came about through an optimization problem without enough constraints. And I always wonder, like, in what environment are we evolving as, like, are our algorithms evolving, and what is the optimization function that encourages us to build these algorithms? And the answer to that most of the time is capitalism. The answer to that is that we're usually, like, if you think of us as a society as an evolving creature, we're usually evolving our tools under the constraint of trying to maximize profit for other people. So that's the framework that I think about this. And then I would usually say that there's been, now we're like the conversation moves away from just what do I do as a data scientist, but what do we do as a society given this optimization problem? Practically, if you're working on technology, I would say maybe there's some bare minimums that have nothing to do with the revolution direction that I was going in just a second ago, that at the bare minimum, we can talk about having the demographics of the team who builds technology could be reflective of the demographics of the people who will use the technology. This might prevent things like producing racist face recognition or imprisonment related software. But again, that doesn't change the overall framework. We could also be doing things like taking the way that we think about threat modeling and the way we try to anticipate how could this go wrong? How could, if somebody got a hold of this, what could be done wrong? What would happen if I was really successful building my machine learning tool, and what if millions of people used this? Or what if the US military used this? This is a way that I could think about whether or not I want to continue or what safeguards I want to put in the way of my research. But again, I think this is applying the brakes to a problem that needs to just be off of the road.
Well, I'm not sure off the road, to be honest. I mean, I've made the point many times, and I'll continue to make it. We are an important profession, both in the data science and more broadly in the software development world. We have a big impact upon the world. And as any profession, we have a responsibility to make sure that impact is good. And I think as an important step is that the most important thing we can do is recognize we have that responsibility. I do run into people who say, well, hey, I don't have a choice, I do what I'm told, kind of thing. That is not an acceptable answer. Well, I mean, it's an acceptable answer to say, yes, I'm just going to do what I'm told, but that doesn't get you out of the responsibility that having what you've done has an effect, and you are responsible for that. And everybody has to in my view, has to draw their own lines about how they make these trade-offs. I mean, yeah, you've got to think about how am I going to pay the mortgage, and these are genuine issues, and you decide what kind of job you want to do. But in the end, you are responsible. That, I think, is the key thing. And I also feel that it's important to realize that you have to be thinking about the benefit you're doing. You don't have to be saving world hunger to be doing something that's beneficial to people. The example I loved, I gave a talk at one point, and somebody said, I don't do anything really worthwhile. I just produce printer software. And before I could even answer, somebody else who was around said, yeah, but that's really valuable. I've just bought a house. If we weren't able to print out all the documents, it would have been so much harder. So they can be small things that are beneficial. But you are responsible for what you do. And that, I think, is the general message that unites all of us in the software world, that we have to be thinking about that.
Yep, definitely. Yeah, to be clear, I don't think that data science is bad. I think it's neither bad nor good, and it's also not neutral. And exactly, we have a responsibility to do things that are not causing harm to other people. And what I really like to think about is what would we build if we were building things that were for the betterment of humanity? And what if we were building things, what would we build if we didn't have to worry about being hungry or being cold if we didn't have a job? And so that's always the way that I try to motivate my thoughts in this topic. I think that there's a lot of good that we can do.
Yes, I certainly hope so. So that hits us pretty much to time, I think, in terms of our sort of planned conversation stuff. So now it's time for Chris to bring in some questions, because I've been completely ignoring the Q&A to concentrate on the conversation.
No, that's fine. We were hoping that you would ignore the Q&A to start with, so to build up the conversation, and then I can read out some now. So the first one that Robert asked was quite a topical one. What's your take on COVID-related data being discussed by the media and politics? It seems that scientists are much more careful in their claims than, I guess, the politics and media.
I gave a talk on lying with data at XConf 2 years ago, I think. And I think you could maybe see that talk from my opinions. I think that there's lots of ways that you can construe data, and it can be for good or for bad. And we should all, like, I guess, like I said earlier, be skeptical and learn to think to discern with our own minds, and actually that was the message of the talk I gave at XConf, was kind of trust no one, but also like move forward with care. And that would be my response.
About it in many ways, because I mean, it's forcing people to confront the reality of messy data that's often uncertain, because, you know, suddenly there's a whole bunch of deaths that we haven't been reporting over the past month, and they all arrive on the same day. So what does that mean? People are beginning to learn about the fact that data comes in these very messy, unwell formulated stuff. I mean, particularly in the US, we're seeing the consequences of different states reporting different things and defining, you know, what do they mean by a COVID infection differently has an effect. And we're also seeing effects like lags in information, and trying to see, from cases, how can you predict hospitalizations? And we're beginning to see the messiness, I think, but also the value of understanding data. And my hope is that it will increase people's motivation to understand what's going on. I mean, it sometimes gets very depressing because you hear people saying so stupid stuff at times. But I really do hope that it will concentrate people to realizing that understanding and getting numerate, getting that core intuition about data is such a useful skill, and that more and more people need to acquire that in order to make sense of the world.
Cool. Thanks very much. Next question is from Ned, who asks, data scientists are increasingly adopting engineering best practices, but there is a friction to this in some organizations due to the siloed nature of the analytics and IT engineering functions. Do you have any thoughts about how these two functions will continue to coexist?
Well, my immediate reaction to any question like that is, well, we need to break down the silos.
Yeah.
And that's kind of been one of my catchphrases for 3 decades or so now. So break the silos.
Yeah, I would second that. I think that we can, sometimes people are reluctant to share out of fear or it's a lack of collaboration mindset. But in any case, the research that we've done in the last 30 years or whatever about how to break down silos within just software world also apply within the data world, though the silos might be taller or more heavily reinforced in some ways.
Makes sense. I guess I'll move on to a related question by an anonymous spectator. How will data science influence the field of computer science in the coming years? I guess, assuming these silos are weakened, what will the effect be on computer science? big questions, I know. I'm asking you to effectively write novels on the spot, but hopefully your reflexive answer will be okay for us.
Yeah, I love to engage in some futurism. I mean, it depends on the scale or the time frame that we're talking about. But I think that in the world of testing, there might be a lot of really nice benefits to have. I think that being able to do generative testing or using randomness in both infrastructure testing as well as user experience or front-end testing, and like this, I think this was the topic of the talk that came right before us. I think that I have an intuitive sense that data science and machine learning algorithms can play an interesting role in that world. I won't speculate any longer into like the world when we have a generalized AI or something like that.
I think one area that is actually currently getting a lot of interest is examination of code bases and code histories and what we can learn from that. So there's a book called Your Code is a Crime Scene.
Mm-hmm.
I can finally remember the name. It's Adam Thornhill who's wrote that book, and he's done some really interesting stuff about examining code and trying to draw lessons from that. And I think that's quite an interesting area. I mean, there's been, the whole time I've been around, a very noisy software metrics crowd, but they've not usually been very good. And I've not been very happy about the quality of most of what has come under metrics. But of course, we have seen some really outstanding work from the State of DevOps report and the Dora work and the Accelerate book from Nicole Forsgren. Former colleague Jez Humble has done some really great work on processes based on that. And that's definitely coming out of that side of thing. Nicole's engagement in that work is really good. And Accelerate was the best book of the year that I had no better than the second best book. So I'd certainly very much recommend the Accelerate book to anybody who's interested in understanding how to improve and look at software practice in an interesting way. So that's another area where data science, and there was a third one as well, but it's gone out of my mind. So maybe I'll just have to shut up.
Yeah, like Mansi talked about Accelerate in the Dora report quite a lot in her talk earlier today. So yes, I think people are familiar with it. Marie has an interesting question, I guess, partly based on the kinds of things books that you've written over time, Martin, which is to ask, do you use test-driven development for testing machine learning models? Does it change your code a lot compared to what you had in your notebook? I guess they're imagining going from a Jupyter notebook to a production code.
Yeah, I would be very surprised if anybody, I guess I would be surprised having a conversation with somebody who says that they do all of their data science test-driven development, because there's so much. I mean, you could maybe write the sanity check or the smoke test or something, like getting the whole pipeline to go through. Start with a really big picture, because that's always going to be quite similar across all the projects. But and certainly doing the transformations of getting data from one shape into another shape, that part I would recommend always to do test-driven development. But if you're doing something that involves data exploration and like augmenting your data, figuring out if adding a new column or removing a new column would be a useful thing for your predictive power, this is almost always going to be done in the Jupyter Notebook first, and I think from what I've seen, rarely tested or begrudgingly tested after that.
Well, I mean,
begrudgingly tested, finishing phrase.
If you know the answer, right, in advance. So if you're exploring, kind of by definition, you can't do test-driven development because you don't know where you're going. But where I would imagine it would be extremely useful is that bit where you talked about taking bits of code out of the notebook and putting them into a much more operationalized, productionized area. Because that, you should know the answer, right? Because you can use the notebook to figure out what the answers are. And so I'd imagine that would be an area where a test-driven approach is going to make a lot more sense.
Yeah, if you could consider having done a bunch of work in a REPL and then writing a test and then getting it to pass in your production code as test-driven development, I guess I wouldn't argue too much with that. Then that sounds like the same framework that I used when I write closure code as well.
So I've actually got a question here about tools. So it's from an anonymous person who says, I know you say framework and tools don't matter. I guess not the most important thing, but they're still curious to know which ones you personally use.
So I use and recommend usually Python and Jupyter notebooks that are using Python as well. For databases, I mean, if that's a question, then that's usually defined by other sorts of business needs. But my usual workflow is Jupyter Notebook, Python, Vim, and anything else I think I'd be flexible on. I also been experimenting with Julia lately, and I really like the Julia language. I still haven't wrapped my head all the way around it yet, and I hear really lovely things about Scala, but it has so many different flavors, and I don't know where to really get started with Scala. I would say if you're using R, I would recommend to people often transition from R into something that can work better in production. Like R, I would call something that you do for data analysis on static files, but if you want to put something into a productive system that's ready to receive queries from REST APIs or something like that, let's go to Python.
I mean, I'm obviously not a proper data scientist. I spend quite a bit of time with R, and I find it really nice as you say, a kind of experimental area. It's kind of weird because in every other programming language I use, I'm always dividing stuff up into functions. And I couldn't tell you how to define a function in R because I do everything through pipeline transformations of the data tables. So once you're doing that, and if you're just doing simple transformations and plots, I find R works really well. I like the R Markdown for similar to the Jupyter Notebook. I gather it's slightly better because it diffs more cleanly in your phone. Also, being an Emacs guy, I use org mode and embed bits of R code and other stuff into org mode, and I find that really nice, but you have to be an Emacs person to enjoy that. Of course, it's wonderful because it's Emacs, but there we are.
Cool. So I have maybe this time for one more question, which this one probably should be for you, Martin. You talked earlier about developing an intuition for kind of statistics and things like that. So if someone wanted to improve their intuition for statistics and probabilities, which board game would you recommend that they spend some time with?
It's an interesting question, and I don't know that there's a good answer for that. I mean, one that which I don't play, but a number of people have recommended is poker. Because poker is all about probabilities and understanding what your odds are. It's also about interacting with people as well, which makes it a very interesting thing. It's never one I've personally gone for, but you do, to get a sense of probabilities, you do want a game where probabilities play an important role in what's flowing through. I did a lot of wargaming when I was younger. I'm constantly looking at combat results tables and assessing probabilities of things. And war games are less like that now. But I wonder to what extent that got me used to the idea that every outcome is just a roll of a die, and I don't know exactly what's going to happen. But if I roll the dice often enough, general trends tend to follow. And how do I kind of tilt things in my direction? But I think there's actually an interesting question more about to what extent one can use probabilistic games to help get people to get that data intuition. But that's just a wild hypothesis that I have not attempted to test. I don't know whether you've got a better idea of that since you actually do this as opposed to dabble in it.
I definitely think you could think of poker as a good way to practice, and yes, indeed, to be learning about statistics, to be able to think like, okay, I have these 2 cards or these 5 cards. What's the probability that other people have certain cards? What's the probability that this next card will come out? And those skills are definitely foundational to the intuition that we're talking about. I think that then it would also require some other, like, maybe that's the practice, and then you also learn theory to get the intuition beyond that, to be able to recognize things like survivor bias, or to understand Simpsons Paradox and how that works.
And I certainly recommend reading Thinking Fast and Slow.
Absolutely.
That was such a good book at picking up many of these kinds of unusual biases and statistical quirks. It's one of those books that's worth reading more than once. Really, really excellent.
Reading once quickly and then once slowly, I guess.
Once quickly. Yeah.
Yep. All right. Thank you both very much for a very insightful chat. I did especially appreciate the kind of the late night TV chat style of it. I think that worked really well after a day of otherwise staring at, you know, people's beautiful and carefully prepared slides. So we really appreciate the insights you were able to bring. So this is actually the last talk of the day. So we're now finished. Both Em and Martin, I think, will be available to hang out on Slack a little bit to answer further questions you might have. I think there's already been quite a bit of chatter there on various topics. Thank you to all our speakers and all our attendees, also the stenographers who toiled away giving subtitles to extraordinarily jargon-heavy talks. I know that can't always be easy, and that's really appreciated. For all our attendees, we're going to actually share a feedback form. So if you are able to give us a little bit of feedback to know how to improve XConf, that would be great. This was the first time we'd ever run it online. Like many organizations, we're kind of feeling our way how to best run things virtually. So if you have suggestions or feedback, we'd love to hear that. We will share the recording soon of all the talks. They'll be freely available. And we'll send out links to the recording to you. Along with the links to the recordings, we'll be offering 50% off registering for XConf next year if you wish to register for the in-person version that will be charged.
We hope.
Sorry, go on.
We hope. Next year,
well,
I'm still thinking it's going to be iffy about next year, I would say.
Well, my linear regression model says that cases are going down in Europe, so hopefully that will be sufficiently accurate for this current purpose. Maybe not XConf US. Let's see.
Yeah, let's see.
One final plug is the next kind of public Thoughtworks event that you might be interested in. They will have another edition of the Tech Radar in November. So if you're interested in that kind of thing and you like the conversation at lunch about the community radar, then tune in for that as well. But for now, that's it for XConf Online 2020. Thank you all so much for showing up and being part of this, I think, quite a successful experiment on running XConf virtually online. See you all.
Thank you very much.
Bye.